telescope more than 1,000,000 miles from Earth is quietly changing everything we thought we knew about the universe. The James Webb Space Telescope has captured details that were once hidden in the depths of time. This year alone, its discoveries have already changed the way we think about the birth of stars and the formation of galaxies several times over. The uniqueness of JWST lies not only in the beauty of the images, but also in the accuracy of the data. Galaxies that once appeared to us as dim spots now reveal their structure, star formation rates, and even the violent processes that govern their evolution. The telescope's unprecedented resolution allows us to peer into the regions where stars are born, giving us a glimpse of the complex interactions that shape the modern universe. In this video, we've compiled the most remarkable discoveries made by JWST this year, each one putting our previous theories to the test, each one bringing us closer to answering fundamental questions about the universe and our place in it. Galaxies and their endless interactions often create strikingly beautiful yet scientifically profound visual images. One such example, observed by the James Webb Space Telescope this September, is the collision of two galaxies known as ARP-107. This event bears an unusual resemblance to a smiling face. The collision, occurring about 465 million light-years away in the constellation Leo Minor, involves a large spiral gateway and a smaller elliptical galaxy. The JWST's near-infrared camera and mid-infrared instrument revealed intricate details that stunned astronomers. Most noticeable in this cosmic smile is the nearly transparent bridge of stars that's been pulled from both galaxies and stretched between them like a thin thread. Areas of active star formation, new stars born from turbulent gases displaced by the merger, glow in orange and red hues. This image tells us about the processes that occur during collisions of this magnitude. Events like this can have two seemingly contradictory effects on galaxies. On the one hand, disruption compresses gas clouds, which accelerate star formation, creating clusters of newborn stars in regions where galaxies collide. On the other hand, collisions can disperse and accelerate gas, depriving parts of galaxies of material which can lead to the starvation of stellar birth in other regions. What's even more interesting is that the large spiral galaxy in this system is classified as a Seyfert galaxy, one of the largest families of active galaxies. Such galaxies have high-energy nuclei dominated by supermassive black holes. In the case of ARP-107, the central region of the spiral galaxy emits energy at a level far beyond that which can be explained by ordinary stars. However, unlike the most active galaxies, Seyfert galaxies such as ARP-107 are less bright, making them easier to study in the infrared spectrum, the main band used by JWST. The collision also sheds light on how such structures evolve under gravitational influence. Despite the event, the galaxy retained much of its overall structure, except for its distinctive spiral arms, which were almost completely obliterated. This observation demonstrates how even off-center collisions can cause significant changes without destroying the entire system. In contrast greatly with the more direct, head-on mergers that typically produce chaotic, irregularly shaped galaxies. ARP-107 today continues its slow gravitational absorption, which will continue for hundreds of millions of years, eventually forming one large, irregularly shaped galaxy. Such things are not uncommon in the universe, but the details that JWST provides allows us to observe and analyze these processes like never before. A little earlier, JWST also shed light on details about another interesting galaxy that has given us important clues about the cycles of birth and destruction that shape the cosmos. Located about 15 million light-years away, M83, also known as NGC 5236, stands out among spiral galaxies not only for its characteristic barred structure, but also for the active stellar processes taking place within it. The center of M83 is a hotbed of star formation, especially visible in the intense blue regions captured in JWST images. Here we see a huge cluster of stars closely clustered together. Even more exciting are its spiral arms extending from the core regions known as stellar nurseries. These regions, where new stars are actively being born, are highlighted in bright yellow and orange colors in MIRI images. They're rich in gas and dust, particularly polycyclic aromatic hydrocarbons, complex carbon-based molecules that often accompany star formation. JWST's ability to detect these compounds is crucial for studying the chemistry of star-forming regions, allowing us to understand the building blocks of the stellar life cycle. By observing M83 at wavelengths between 5,000 and 28,000 nanometers, Webb can penetrate through the dust that normally hides these stellar nurseries from optical telescopes. These detailed images provide a fundamental tool for understanding the process known as stellar feedback, how young, newly born stars interact with their environment. When forming, stars release energy and eject material in the form of stellar wind and radiation. This feedback can either compress nearby gas, triggering further star formation, or disperse the gas, stopping the birth of new stars in surrounding regions. By carefully studying galaxies like M83, researchers working on programs such as Feedback and Emerging Extragalactic Star Clusters, or FEAST, seek to unravel how such feedback mechanisms operate in different galactic environments. The results obtained on M83, as well as on other galaxies in the FEAST program, will help refine the models that astronomers use to simulate star formation throughout the universe. Another JWST observation of the N79 Nebula, this time in January, has presented us with one of the most active star-forming regions in our galactic neighborhood. Located about 161,000 light-years away in the large Magellanic Cloud, N79 is a prime example of a star factory, where new stars are forming at a highly accelerated rate. Unlike its better-known neighbor, the Tarantula Nebula, N79 has remained relatively unexplored until now. The striking starburst pattern emanating from nebula's core is immediately apparent in the JWST image. This effect is not an intrinstic feature of the nebula, but rather a consequence of the way JWST's segmented primary mirror collects light from particularly bright objects. These diffraction peaks emphasize the intense light of a young forming star, barely visible in the visible wavelength range, but revealing through the power of infrared observation. The orange and red regions surrounding this core are huge clouds of molecular gas, the raw material from which new stars form. In these regions, massive clumps of cold hydrogen gradually condense under the action of gravity, triggering the star formation process. Protostars, still in their native gas envelope, are particularly important for understanding stellar evolution. They represent the initial stage of a star's life when nuclear fusion has not yet begun in their cores. A mass is gained from the surrounding gas envelopes. They'll eventually reach a point where the internal pressure and temperature become sufficient for hydrogen to fuse into helium, officially marking the birth of a full-fledged star. Another exciting aspect of the discovery of the N79 Nebula is its potential to shed light on the early universe. By studying local processes, astronomers can gain insight into the conditions that prevailed during the most intense period of star formation in the cosmos. Also this June, Webb gave us another interesting example of star formation by observing the spectacular Serpens Nebula. In this region, located about 1,300 light-years from Earth, a remarkable phenomenon has been observed. Protostellar outflows, jets of gas erupting from young stars. Although such outflows have been observed before, the accuracy and clarity left much to be desired. These jets represent one of the earliest stages of a star's development. When the gas collapses under gravity to form a protostar, some of the material is trapped in jets that fly out of the star's poles at incredible speeds. However, the unique arrangement of these jets in the Serpens Nebula provides new insights into a process that until now could only be hypothesized. The jets flowing in the same direction provide strong support for the long-standing theory that stars forming in the same region orbit in the same direction. What makes this discovery even more significant is the permanence of this alignment, which NASA scientists have likened to sleet falling during a storm. This metaphor emphasizes the striking orderliness in the chaotic environment of star birth. The implication's obvious. These aligned flows serve as a kind of historical record of the rotational dynamics in the gas and dust clouds. As stars form, they inherit the angular momentum of the collapsing cloud, which leads to synchronous motion. One of the most striking aspects of this photo is the appearance of an hourglass-shaped shadow cast by one of the young stars. This shadow is a direct result of the jets giving the surrounding gas such a striking shape. JWST's nebula observations are not just limited to star formation. They also provide crucial information about the evolution of the disk and material surrounding these young stars, key ingredients for planet formation. By capturing these jets so early in the development of stars, astronomers can begin to piece together the complex processes that lead to the creation of planetary systems. But Webb's June discoveries don't end there. WSP-39b, a gas giant located 700 light-years from Earth, represents one of the most intriguing planetary environments ever observed. Thanks to the unprecedented sensitivity of the Space Telescope, we now have a clearer picture of the extreme climate of this exoplanet, a world divided between eternal day and endless night. This exoplanet is in tidal lock, meaning that one side of it is always facing the star and basking in the sun's rays, while the other is in perpetual darkness. This sharp separation creates a unique atmospheric environment that precisely rejects the possibility of life and takes our understanding of planetary climate dynamics to a new level. The JWST near-infrared spectrograph allowed astronomers to measure the temperature differences in these regions with an astonishing level of detail. At first glance, it may seem like a world of absolutes, scorching heat on one side and icy cold on the other. But the real allure lies in the so-called gray zone between these extremes, where the temperature transitions from the day side to the night side. NIRS spec data shows that the temperature difference between the dawn and twilight regions is an impressive 300 degrees Fahrenheit. On the dawn side, the temperature stays around 1,150 degrees Fahrenheit and rises to about 1,450 degrees Fahrenheit in the evening. JWST also discovered impressive weather patterns on the exoplanet. Wind sweeps across the surface at astonishing speeds of thousands of miles per hour, transferring heat from the day side to the night side. And this atmospheric circulation is critical to maintaining the balance of temperature on the planet. Interestingly, the dawn side, where night turns to day, tends to be more cloudy. Thick layers of gas form in this colder region. In contrast, the evening side, where day turns to night, appears much clearer, with fewer clouds, perhaps a result of the warmer temperatures displacing condensed gases. These discoveries challenge previous models of exoplanet atmospheres, especially on worlds in tidal capture. Understanding how atmospheric circulation, temperature variations, and cloud formation act on WST-39b provides insight into how planets with extreme climates can evolve. More importantly, it opens new avenues in the search for potentially habitable planets, as scientists can apply these observations to smaller, rocky exoplanets that may have similar gaps between day and night. By precisely measuring the composition of its atmosphere, JWST has detected trace amounts of molecules such as water vapor, carbon dioxide, and sulfur dioxide, giving us insight into the chemical processes that take place on similar planets. This detailed analysis of the atmosphere is of great importance to the search for life beyond Earth, as it allows astronomers to improve their methods for detecting biosignatures. A month later, in July, Webb pleased with another discovery. This study, published in the monthly notices of the Royal Astronomical Society, concerned brown dwarfs, but this time was more extensive. Brown dwarfs, often referred to as failed stars, occupy an interesting intermediate position between planets and stars. Although they lack the mass to ignite nuclear fusion in their core, their atmospheres are far from quiet. The James Webb Space Telescope recently allowed us to study in detail the chaotic weather systems of two nearby brown dwarfs, WISE 1049a and WISE 1049b. These observations have given us a rare glimpse into the atmospheric processes of these enigmatic objects and hint at what we can expect from giant exoplanets with similar conditions. The weather here is far from ordinary. Infrared instruments have shown that both objects are engulfed by colossal, turbulent clouds composed of silicate grains, essentially hot sand swirling in the atmosphere. These clouds, fanned by winds moving at tremendous speeds, create a dynamic environment with temperatures ranging from 1,610 degrees Fahrenheit to 1,880 degrees Fahrenheit. Both bodies rotate at an astonishing rate. WISE 1049a completes a full revolution every 7 hours, and its brother B even faster, in 5 hours. This rapid rotation contributes to the extreme variability observed in their atmospheres. However, the observations do allow us to see how the atmospheres change over time. JWST has taken pictures of the light curves of these brown dwarfs, which show significant variations, indicating stormy weather conditions and shifting cloud cover at different altitudes. The light curves obtained with JWST show how clouds evolve at different altitudes, sometimes exposing deeper layers of the atmosphere through gaps in the cloud cover. These variations are associated with different chemical compositions at different depths of the atmosphere. By examining specific wavelengths of light, JWST has found evidence of carbon monoxide, methane, and even silicate grains absorbing into the atmosphere. Each of these chemical markers tells a story about temperature and pressure at different depths, offering a vertical profile of brown dwarfs' atmospheres. Observations indicate that each brown dwarf has 3 distinct atmospheric layers. The deepest layer emits light with wavelengths of less than 8.5 microns, while the intermediate layer absorbs light in the range of 2.3 to 4.2 microns. The uppermost layer, where silicate clouds are most visible, emits signals between 4.2 and 8.5 microns. These results have allowed scientists to study the dynamic nature of brown dwarf atmospheres in unprecedented detail, which was not possible with previous observations. And more importantly, refine models that will help us understand the atmospheres of distant exoplanets, especially those that are too far away to study in such detail. Among the many spectacular images taken by the James Webb Space Telescope, one stands out not only for its beauty, but also for the questions it raises, literally. Against the stunning observation of star formation, a distant object resembling a question mark stands out in bright red. This unexpected shape, also captured this July, is most likely the result of an interaction between the galaxies of the Herbig-Haro 4647 complex. Although visually striking, the object's true nature remains a mystery. Initial analysis by scientists at the Space Telescope Science Institute suggests that it's likely a distant galaxy or possibly two galaxies in the process of merging. The red hue of the object in the near-infrared JWST image indicates that it is incredibly far away, perhaps billions of light years from Earth. This distance not only makes it difficult to study the object, but also places it in a period of the universe's history when galaxy interactions were more common, as galaxies were still forming and evolving. Galaxy mergers are a powerful cosmic phenomenon that can change the shape of galaxies, creating long, curved tidal tails and arcs. These features are formed as the mutual gravitational forces of galaxies stretch and distort their outer regions. The shape of the question mark may be a similar result of tidal interactions. The curved upper part represents a galaxy being pushed apart by gravitational force, while the lower point is possibly a smaller companion galaxy. The formation of galaxies, especially in the early universe, remains one of the deepest mysteries of cosmology. Webb's observations have provided new insights into this process, especially in the case of three galaxies discovered earlier this year that formed between 400 and 6 million years after the Big Bang. In the early days of the universe, neutral hydrogen gas filled the cosmos, forming a thick opaque fog. When galaxies like those observed by JWST began to form, their light helped lift this fog, eventually revealing the modern universe to us. These galaxies have not yet fully formed, but they're still feeding off nearby clouds of gas, mostly hydrogen and helium, the basic building blocks for star formation. Infrared capability allowed astronomers to observe how this gas is absorbed by galaxies, providing a direct view of the galaxy formation process. One of the most remarkable aspects of these galaxies is their association with powerful satellite jets. During the formation of galaxies, their central regions often host supermassive black holes that exert an intense gravitational influence on the surrounding space. When matter falls toward the black hole, some of it's accelerated and ejected as powerful jets hurtling through space at nearly the speed of light. These jets, often observed in young galaxies, play an important role in regulating star formation, as they can either stimulate or suppress the formation of new stars depending on how they interact with the surrounding gas. Three recently discovered galaxies are particularly interesting because they can provide insight into this process at a very early stage in the history of the universe. In these galaxies, jets from nascent supermassive black holes should still be interacting with the surrounding primordial gas, but not yet have had time to fully trigger the star formation process. Probably these galaxies are in a transitional phase, on the threshold of the birth of the first generation of stars. This process should take millions of years. These observations are particularly interesting because they are the first direct images of galaxy formation ever obtained. Before JWST, speculate about how galaxies form by studying more evolved systems. Now, for the first time, we can observe the earliest birth stages of their growth and evolution, and how the interactions of gas, stars, and black holes shape the universe. As the James Webb Space Telescope continues its mission, each new discovery changes our understanding of the universe. From the birth of stars to the mysteries of distant exoplanets, JWST not only answers age-old questions, but also opens up entirely new ones, pushing the boundaries of our knowledge. Continued research and exploration are crucial. We look to the future and the coming discoveries that will inspire new generations to keep looking, asking questions, and reaching for the stars. More than 30 times farther from the sun, almost at the edge of our solar system, there's one mysterious planet, Neptune. It's impossible to see it, even from the highest points on Earth without a telescope. Because of its remoteness, Neptune is the least explored planet in our entire system. But what could be so mysterious about this planet? Would you be surprised if we told you that Neptune, one of the coldest planets in the system, can support an ocean of super hot water? Today you'll learn about that, as well as Neptune's strange rings, what makes it so blue, and also what is now known about its famous satellite, Triton. Neptune is an ice giant, about 4 times wider than Earth. It has a radius of about 15,300 miles and a volume of 15 trillion miles cubed, which means that Neptune is 58 times larger than Earth in volume. The planet is composed mostly of water, methane, and ammonia. Like the other ice and gas giants in our system, Neptune has no solid surface. Its atmosphere extends deep into the planet to the mantle, which is composed of methane and ammonia ice and a rocky core. Nevertheless, scientists believe that the ice giant could theoretically have an internal hot ocean. But how can a planet sustain such an ocean since it's so far from the sun? It would take sunlight 4 hours to reach the giant's surface. Neptune's average atmospheric temperature is negative 360 degrees Fahrenheit, making it one of the coldest objects in the solar system. In addition, according to recent research, most of Neptune cooled from 2003 to 2018, despite warming near the South Pole from 2018 to 2020, likely due to seasonal changes in atmospheric chemistry. The reason for the likely formation of the ocean inside the ice giant remains unsolved. However, scientists suggest that this strangeness can be explained by internal heating. Heat released due to gravitational compression or gravitational interaction between Neptune and one of its satellites, Triton. On the other hand, researchers Sloan Viktorovich and Andrew Ingersoll believe that the probability of oceans on Neptune due to its heat is very low, only 15% at this time. According to scientists' calculation, only in 1 billion years will the chance of an ocean there increase to 40% after the giant cools down. Another explanation for the huge internal energy could be Neptune's collision with some cosmic object, because Neptune is the only planet that emits nearly 3 times as much energy as it receives from the Sun. This is also confirmed by the unusual 28-degree tilt axis, almost as much as on Earth. Because of this, Neptune also experiences seasons similar to ours, but on Neptune, one season lasts about 40 years. 1 year for Neptune is 165 Earth years. Yet 1 day on the ice giant takes 16 hours. This rapid rotation of the planet creates super powerful wind, which we'll talk about a little later. Neptune's atmosphere is 80% hydrogen. It also contains 19% helium and about 1% of other gases, including methane. By the way, Neptune's blue color is caused precisely by methane clouds in the upper layers of the atmosphere. Methane molecules can absorb solar shortwave radiation, reflecting the blue color. However, the nearest planet to Neptune, Uranus, also contains a similar distribution of gases. But unlike Neptune, the color is pale blue. Dr. Patrick Irwin of Oxford University suggests that this color difference may be due to the density of methane fog. Thus, the atmospheres of both planets have several aerosol layers. The bottom deep layer consists of a mixture of hydrogen sulfide ice. It's because of this layer that some areas can be seen closer to the poles. For example, they appear darker on Neptune. The second layer is probably just what affects the colors of the planets. It's a layer of haze particles in which methane ice probably forms. The ice then precipitates as a rain of methane snow. Since Neptune's atmosphere is much more active than that of Uranus, Neptune forms this snow more efficiently, so its second aerosol layer is thinner. It is precisely the lower density that causes this rich blue color. The last third atmospheric layer also forms large particles of methane ice and is, in fact, an extension of the second layer. In addition to its intense color, Neptune is also characterized by dark and white patches all over its surface. All of these spots are storms resulting from the planet's very rapid axial rotation. Neptune is the windiest planet in the system. Wind currents there can reach 1,200 miles per hour, which is almost 4 times stronger than Jupiter. However, the ice giant has one similarity with Jupiter, a huge storm. The name of this vortex is simple enough: the Big Dark Spot. The Earth-sized cyclone orbiting at 1,500 miles per hour was first detected by the Voyager 2 spacecraft in 1989. However, in 1994, another telescope, the Hubble, noticed the spot had disappeared and a small new spot appeared in the northern hemisphere. So unlike the 300-year-old cyclone on Jupiter, Neptune's large-scale vortices only exist for 2 to 6 years. In 2018, Hubble detected another new spot similar to the one discovered in 1989. The formation of these storms is still unknown, but scientists suggest they originate deep in the atmosphere, forming over several years. These storms still have something to show scientists. The new 2018 spot began drifting southward the following year, where it would have disappeared. However, unexpectedly for researchers, the storm turned around and began moving back north. What's more, a small one probably separated from the big spot. NASA scientists believe the small vortex may be part of the process of breaking up the big storm, which has never been observed before. Such cyclones in previous observations have been accompanied by white methane clouds called scooter because of the speed of motion greater than that of the big spot. They probably form over vortices, where gases freeze into ice crystals. The lack of clouds, the researchers say, may help in understanding the formation of patches on Neptune and similar ice giants. Like other gas giants, Neptune has another feature, a ring system. In 2022, The James Webb Space Telescope took a near-infrared image of the icy giant, showing its faint rings and satellites. The last image of Neptune's rings was taken more than 30 years ago by Voyager 2. In Webb's new photo, about 5 rings can be seen. All rings are named after astronomers who have contributed to the study of Neptune. The closest and most loose ring is called Halley. It consists of about 40% to 70% dust and is 26,000 miles and has a radial width of 1,240 miles. The second ring of Leverrier is much brighter, much narrower. Its width is a little over 62 miles. The next ring is the widest of all. This is the Lassell ring, 2,485 miles wide. The percentage of dust there is very small, ranging from 20% to 40%. The fourth, Arago ring, is hard to see. It is one of the smallest rings with a radius of 35,540 miles. And it's on the edge of the Lassell, and probably because of its low dust content, is hardly noticeable. The last, Adams ring, has an orbital radius of approximately 39,724 miles. Moreover, Adams is only 35 kilometers wide, making it the narrowest ring of Neptune. But what makes this ring stand out in its arcs? The arcs are mysterious bright seals of dust around the perimeter of the ring. Each of Adam's arcs has a name: freedom, brotherhood, courage, and equality. Interestingly, they are not static at all. These arcs, especially brotherhood and equality, exchange their material and change their size. Why these arcs formed is still unknown, but researcher Imke de Pater suggests that the cause may be the collapse of a parent companion or other object in the Roche limit. In addition to the rings, Webb also recorded 7 of Neptune's 14 satellites. All of the ice giant's moons are divided into regular and irregular. Webb captured 6 ordinary inner satellites. Some of these satellites, like Despina and Galatea, form Neptune's rings, playing the role of shepherd for dust. However, definitely the most interesting thing in Webb's image is the most distant bright satellite, Triton. In the photo, Triton looks like a star because it glows much more than Neptune. The strange glow is because the satellite is almost completely covered by nitrogen ice and therefore reflects about 70% of all sunlight that falls on its surface. Triton is Neptune's largest satellite. It is larger even than Pluto. It has a diameter of 1,680 miles, which can be equated to 99.7% of the mass of all Neptune's moons. It is also the coldest geologically active object in the entire solar system. Its surface temperature reaches negative 391 degrees Fahrenheit just because of its light-reflecting icy surface. Like any of the moons of the ice giant, Triton experiences wave blocking, meaning that only one side of it is turned toward the planet. However, its retrograde orbit sets it apart from other satellites, which is unusual and unique to all other satellites in our system. That means that Triton has an inclined orbit, which causes it to move in the opposite direction to Neptune. Also, because of this orbit, its poles and equator alternately face the sun. But what could have caused such an unusual orbital tilt? Most likely, Triton never formed with Neptune. Scientists believe that Triton originally evolved in the Kuiper Belt, but at some point it was able to be captured by an ice giant, and it's assumed that Triton could hypothetically move around another object. Therefore, the captured Triton slowed down, which prevented it from colliding with Neptune. Moving toward Neptune, the satellite could also destroy other moons. Neptune has very few satellites compared to, for example, Jupiter, around which there are almost 70 objects. There probably could have been more, and they would have been larger, had not Triton been captured by the giant's gravitational pull. Triton's features don't end there. If you look closely at pictures taken back in 1989 by Voyager 2, you can discern the satellite's unusual mosaic surface, modeled with plumes. According to the analysis of the craters by scientists, their surface could be from 10 million to 100 million years old, and in some places, the smooth surface on the manifestation of cryovolcanism. Therefore, scientists believe that the moon may have a subsurface ocean. The plumes also probably hint at this and also depict a depression similar to a lake basin. Despite its low temperature, Triton probably retains a lot of ammonia beneath its surface, which slows the freezing of the water. On the other hand, plumes may appear due to heating by sunlight, causing nitrogen to compress beneath Triton's icy surface until the nitrogen escapes. At this point, proving that the satellite could be an oceanic world is very difficult. In addition, solar heating probably forms the moon's thin nitrogen atmosphere. However, the possibility of life developing there, as on presumably Enceladus, is too early to tell. Given that Triton was part of the Kuiper Belt, does this mean that Neptune can influence its objects? The Kuiper Belt is the boundary of our solar system, also the comet's source. The belt extends from Neptune 30 AU by about 20 AU. The belt is predominantly composed of small objects like asteroids and tens of thousands of more large objects, including dwarf planets like Pluto. Were it not for the gravitational influence of an ice giant, it's likely that a planet could have formed from the Kuiper Belt. In addition, scientists have noticed that some objects in the belt, including Pluto, are in long-range resonance with Neptune. Usually such objects, planetesimals, can only temporarily come into resonance with a stable, fixed-in-one-place planet. Therefore, scientists suggest that it's likely that Neptune may have migrated from the inner regions of the solar system, meaning that it may have originally formed close to the Sun. Thus, the migration of the ice giant was probably able to keep many Kuiper Belt objects within the solar system, when, without resonances, gravitational effects could have pushed them outside the system and even in our direction. Neptune definitely has many unexplored mysteries. At this point, we don't know, for example, the exact composition of Neptune's interior, or in general how ice giants are formed. So we have to wait for future scientific expeditions that will help us better understand the chemistry of these worlds and unravel many of the mysteries that interest us. Do you think it could be that one of the most fundamental aspects of our lives is nothing more than a complex illusion? Time, the omnipresent force that apparently governs our existence and dictates the rhythm of our lives, is not what it seems. For example, time appears to be slowed down for an object moving close to the speed of light, and it flows at different speeds depending on the strength and the gravitational field around us. Have you ever considered that time may be just a figment of our imagination, a construct invented by our brains to make sense of the world? In search of the truth behind this mysterious concept, you'll have to step into the unknown and question everything you thought you knew about time. Time, in its simplest form, is a tool we created to measure change and put order into the complex events that make up our lives. Our ancestors needed a way to keep track of natural cycles such as day and night, or the changing of the seasons. This was crucial to the coordination of activities such as farming, navigation, and religious rituals. Early methods of timekeeping were based on natural phenomena, such as the rising and setting of the sun, the phases of the moon, and the position of the stars. As human society became more complex, so did our methods of measuring time. We developed tools such as sundials, water clocks, and finally, mechanical clocks to divide the day into smaller and more manageable parts. Calendars were created to track the passage of longer periods such as months and years. Different cultures have developed their own unique calendars and timekeeping systems, reflecting the diversity of human understanding and interpretation of time. While timekeeping systems help us manage our daily activities and long-term planning, the perception of time remains a deeply personal and subjective experience. Our brains process and interpret time differently depending on factors such as age, emotional state, and cultural background. This suggests that time is not a specific universal phenomenon, but rather a flexible construct that we shape according to our individual experiences and needs. Despite its ubiquitous presence in our lives, time remains a somewhat illusory concept. This raises the question, is time an objective reality, or is it simply a construct we've created to order the chaos of our existence? So let's delve a little deeper into history. The traditional understanding of time as an independent, constant entity was challenged by a groundbreaking work from the early 20th century written by Albert Einstein. Einstein's theory of relativity introduced the concept of time as a dimension, forever changing our view of this mysterious phenomenon. Einstein's theory of relativity emerged from his work on the nature of light and the concept of absolute space and time, which was central to classical physics. He proposed that the law of physics should be the same for all observers, regardless of their motion relative to each other. This revolutionary idea led to the development of two interrelated theories, the special theory of relativity and the general theory of relativity. In the special theory of relativity, Einstein demonstrated that space and time are not separate entities, but intertwined in a single continuum known as space-time. In this four-dimensional structure, time becomes the fourth dimension, and events are represented as points in space-time. This concept shattered the traditional view of time as an independent variable by showing that it is an integral part of the fabric of the universe. Einstein's theories also showed that time is relative and dependent on the observer's frame of reference. According to the special theory of relativity, two events that appear to be simultaneous to one observer may occur at different times to another observer moving relative to the first. This phenomenon, known as simultaneity relativity, challenges our perception of time as an absolute and constant entity. The general theory of relativity extended the ideas of the special theory of relativity to include gravity in the picture. In this theory, massive objects such as planets and stars cause space-time to warp, and this warp is perceived by objects moving within it as gravity. The presence of a massive object can also affect the flow of time, leading to a phenomenon known as gravitational time dilation. In the special theory of relativity, time dilation occurs when two objects move relative to each other with considerable speed. The faster an object moves, the slower time flows for that object compared to a stationary observer. This effect becomes more pronounced as the object approaches the speed of light. This phenomenon is best illustrated by the famous twin paradox, where one twin travels at near the speed of light, while the other stays on Earth. Upon return, the traveling twin will be younger than the Earth twin because of the time dilation. In general relativity, time dilation is also due to the influence of gravity. Time flows more slowly in stronger gravitational fields, for example, near massive celestial objects such as planets or stars. This effect has been experimentally tested using atomic clocks placed at different heights. Clocks closer to the Earth's surface, where gravity is stronger, run slower compared to clocks at a higher altitude, where gravity is weaker. The slowing of time, while seemingly illogical, has been confirmed experimentally and has practical applications. An excellent example is the Global Positioning System, or GPS. GPS satellites orbiting the Earth experience time dilation based on both velocity and gravity, which must be taken into account to maintain accurate timekeeping and location data. In addition, experiments with high-speed particle gas pedals have confirmed that particles traveling at near light speeds experience significant time dilation, as predicted by the special theory of relativity. Before Einstein's theory of relativity, time was assumed to be unchanging and a universal background for all events in the universe. Sir Isaac Newton, for example, believed in the concept of absolute time, which flows uniformly and independently of the events he measures. However, the discoveries of time dilation and the relative nature of time in both the special and general theories of relativity challenge this concept, demonstrating that time is not a constant but a variable, depending on the motion of the observer and the surrounding gravitational field. The traditional view of time as an absolute entity also assumes a strict adherence to causality, where cause always precedes effect. However, the relative nature of time in relativity theory suggests that the order of events may depend on the observer's frame of reference, which can lead to situations where cause and effect may appear to be reversed or simultaneous. This challenges our intuitive understanding of causality and forces us to re-evaluate how we think about the evolution of events in the universe. The concept of the arrow of time, the idea that time flows in one direction from past to future, it's deeply rooted in our understanding of the world, has also been challenged. However, the findings of relativity theory regarding the relative nature of time and the potential reversal of causality prompt us to reconsider whether the arrow of time is a fundamental aspect of the universe or simply a construct of human perception. Since the traditional as an absolute entity has been undermined by the discoveries of the relativity theory, some scientists and philosophers have suggested that time may be an emergent property rather than a fundamental aspect of the universe. From this perspective, time arises from interactions and relationships between objects and events, rather than existing independently. Leaving behind the challenges of Einstein's theory of relativity, we venture into the even more confusing world of quantum mechanics. In this realm, the nature of time becomes confusing and elusive, as the rules governing the quantum world defy our everyday understanding. Quantum mechanics is a branch of physics that studies the behavior of particles at the atomic and subatomic levels. It's governed by a set of probability rules that are markedly different from the rules of classical physics. In the quantum world, particles can exist in several states simultaneously, a phenomenon known as superposition, and their properties are defined only when they're measured or observed. The concept of time in quantum mechanics is very different from the concept of time in classical physics. While classical physics described time as a continuous and absolute entity, quantum mechanics treats it as a discrete, quantized parameter. This leads to situations where it seems that time loses its traditional meaning and takes on a more abstract role. Now, to illustrate, let's consider the following everyday scenario. You observe animals in the wild and notice they behave differently when they know they're being watched. The closer you get to them, the more their behavior changes, making it difficult to understand their natural state. This example illustrates the observer effect in quantum mechanics, also called the Heisenberg uncertainty principle. In the context of quantum mechanics, the observer effect refers to the idea that active measurements or observations can disturb the state of a quantum object such as an electron, just as your attempt to observe animals in the wild affects their behavior. Observing or measuring a quantum object can affect its properties, such as position or momentum. Heisenberg's uncertainty principle states it's possible to simultaneously know the position and momentum of a quantum object with absolute accuracy. The more precisely we measure one property, the less precisely we can know the other. In the quantum world, the very act of observation or measurement can lead to the collapse of the wave function of a particle and the transition from the superposition of many states to one definite state. This process is inherently probabilistic, and the result cannot be predicted with certainty. Taking into account the phenomena of quantum superposition and observer effect, it becomes obvious that our traditional understanding of time as linear progression may be wrong on the quantum level. Instead, the quantum world offers a more fluid, interconnected view of time where the boundaries between past, present, and future are not as rigid as we once thought. As we've seen, our understanding of time is closely intertwined with our understanding of space, and this complex relationship has given rise to many theories attempting to explain the nature of space-time. Among these theories, one stands out as particularly intriguing and thought-provoking: the block universe theory. The block universe theory, also known as eternalism or the space-time block view, is a philosophical concept that stems from our understanding of Einstein's theory of relativity. According to this theory, past, present, and future are not separate entities, but part of a single four-dimensional structure called space-time. In this structure, all events from the origin of the universe to its possible end coexist simultaneously. To better understand the theory of the block universe, we must first understand the concept of space-time. In Einstein's theory of relativity, space and time are intertwined, forming a single continuum. Space-time can be thought of as a vast four-dimensional block containing every event that has ever happened or will happen. In this situation, time is not a separate dimension that flows linearly, but rather an integral part of the space-time structure. Each point in space-time represents a unique event, and all space-time encompasses all possible events. Consequently, past, present, and future coexist in a block universe, turning our perception of time as a linear progression into an illusion created by our limited perspective. In the block universe theory, observers play a crucial role in the perception of the flow of time. Our perception of time as a linear progression from past to present to future is the result of the movement of our consciousness along our world lines, the paths we trace in space-time. Although all events exist simultaneously in the block universe, our subjective sense of time is limited to a single point on our world line, the present moment. This subjective sense of time can be likened to reading a book. Although all the words and sentences exist simultaneously on the pages, our perception of history is sequential, revealing one word at a time. Similarly, the events of our lives unfold as we cross our world lines with the block universe. Block universe theory also raises thought-provoking questions about the nature of free will. If all events, including our thoughts, decisions, and actions, are predetermined and exist simultaneously in space-time, does this mean that our choices are predetermined and free will is an illusion? This question has been the subject of heated debate among philosophers and scientists alike. Some argue that the existence of free will is compatible with the block universe theory, since our choices can still be determined by our internal processes, even if the results are already fixed in space-time. Others argue that a block universe implies a deterministic universe where our actions are simply the result of the laws of physics and the concept of free will is an illusion. Not only does the theory of the block universe challenge our understanding of time and causality, it also raises profound questions about the nature of reality itself. If all events coexist in space-time, does this mean that reality is a static, unchanging structure? Or is our perception of reality, including the subjective flow of time, an essential aspect of the universe that cannot be separated from the objective structure of space-time? These questions go to the heart of our understanding of the nature of existence. By exploring the implications of block universe theory, we may be forced to reevaluate our perceptions of time, causality, free will, and reality itself, opening the door to a new understanding of the fundamental nature of the universe. In our daily lives, we rely on the passage of time to structure our activities, make sense of the world around us, and create meaningful accounts of our experiences. Time allows us to growth and decline, and to make predictions guided by past events. At the same time, our study of the nature of time has shown that our perception of time as a linear progression may only be a simple illusion, the product of our limited perspective in the vast fabric of space-time. This paradoxical nature of time is a fascinating enigma. Time is both an important aspect of our lives and a construct that may not exist as we perceive it. Either way, we must remain open to new ideas and perspectives, for it's through our curiosity, our willingness to question the nature of reality, and our relentless pursuit of knowledge that we will continue to discover the mysteries of time and the universe itself. Every few years, the seemingly calm Pacific Ocean hides a secret. Beneath its surface, a powerful force is raging, a climactic phenomenon that affects weather conditions around the world. Its name is El Niño. From torrential rains that cause catastrophic flooding in South America to severe droughts that cause wildfires in Australia, El Niño is not just a tropical oddity. It is a global disruptor. But what causes this climate phenomenon? Let's find out. El Niño, which means the boy in Spanish, affects the water in the ocean, heating it by about 32.4 to 32.9 degrees Fahrenheit above the average temperature. It was first recorded in the 16th century. This phenomenon can be observed in all parts of our planet. El Niño can lead to floods, droughts, increased levels of CO2, and global temperature changes. It begins to spread from the east-central Pacific Ocean. Therefore, developing countries bordering the ocean and marine life that is not prepared for abrupt climate change suffer the most from the sharp heating of water. However, El Niño is not the only phenomenon that can affect global weather. In fact, El Niño is just a phase of a single climate phenomenon called the El Niño Southern Oscillation. This cycle can be in two other phases. One of them is La Niña, which is the exact opposite of El Niño. And the other is a neutral state where there's no particular influence of either of them. La Niña, or the girl in Spanish, is a weather phenomenon that causes cooling rather than heating of water. In general, the water temperature during La Niña decreases by as much as 37 to 41 degrees Fahrenheit. The consequences of this phenomenon for many countries around the world, such as the United States and Canada, are severe rainstorms, floods, and stronger hurricane seasons. But the worst part is that these two phenomena are very difficult to predict, and therefore to prepare for. They occur every 2 to 7 years, so they're not regular. Moreover, they're not short-term phenomena. El Niño lasts about 9 to 12 months, while La Niña usually lasts 1 to 3 years. El Niño and La Niña do not appear out of nowhere. Their formation is a very unusual process. Under normal conditions in the Pacific Ocean, trade winds move from a high-pressure zone to a low-pressure zone from east to west. These winds direct warm water in the direction of their own movement closer to Asian countries and Australia. Thus, cold water rises in the east, on the coast of South America, which also has a positive effect on fish catch due to the saturation of such water with nutrients. This process is called upwelling. Warm water warms the air, which causes it to rise faster into the lower atmosphere and condense, while cooler air returns to the eastern parts, thus supporting the trade winds. However, if this balance is somehow disturbed, then El Niño or La Niña begins. During El Niño, the winds weaken, so the warm water is not affected by the wind movement to a large extent, and upwelling also decreases. Consequently, the water in the Pacific Ocean begins to heat up evenly in normally cold areas. This in turn means that rains are also changing, causing dramatic weather changes in all parts of the world. For example, in the tropics, the chance of flooding increases, and in western countries, droughts increase. As an example, we can cite the protected area in Hawaii, Pu'awawa. Under typical conditions, the average rainfall there is about 2.7 inches in January, but under El Niño conditions in 2010, only 0.4 inches fell there. However, over time, one place of ENSO can change to another, such as La Niña. During La Niña, the winds, on the contrary, become stronger, which increases upwelling and reduces the areas of warm water in the ocean. So, for example, the western parts of the United States and northern parts of South America may experience cooling, while areas in the Indian Ocean may experience warming. Consequently, the regions bordering the Pacific Ocean suffer the most from these phenomena. Approximately 30 to 60 million people died due to severe drought and floods in India, China, and Brazil in the 19th century. In the 20th century, 26 cases of El Niño were recorded, which seriously affected the harvest of Western countries, and in addition, the population of various animals, including sea lions. Thus, the main victims of El Niño are such South American countries as Peru and Ecuador. Most of the economy of these countries depends on the export of fish and fertilizers. However, due to El Niño, upwelling decreases, which leads to massive fish kills, and precipitation increases, so crops and fertilizers are washed away and civilian infrastructure is damaged. On the other hand, droughts are looming in eastern regions such as Indonesia and Australia. Because of this, water bodies and crops are beginning to dry up, which negatively impacts the standard of living and health of people and animals, as well as land fertility. African eastern countries such as Kenya or Tanzania, as well as American countries, suffer from frequent rains, while South Central countries like Zambia or Mozambique suffer from drought. The South United States, in particular Texas, also suffers from increased precipitation during El Niño. However, for example, in California, the phenomena brings rain, which has a positive effect on the harvest of crops like lime and avocado. In particular, Canadian winters are becoming milder. Interestingly, El Niño also affects Antarctica. In its western part, it becomes a little warmer, so more snow falls, but due to a decrease in upwelling, shelf glaciers begin to melt. On the other hand, La Niña helps to increase the mass of these glaciers, which helps to maintain the balance. The direct impact of ENSO on European countries is difficult to document. El Niño brings cold and dry winters to the European continent, which can be harmful to the land. For example, in the 18th century, El Niño greatly affected the harvest of European countries, which was also probably one of the reasons for the outbreak of the French Revolution in 1789. Already in the 19th century, this phenomenon caused about 3 severe famines in various Asian and European countries. So El Niño and La Niña are quite dangerous phenomena for our world. The last time El Niño and La Niña were observed was in 2015 and 16, almost 7 years ago. 2016 was the hottest year on record. It was the most severe of all previous El Niño episodes in the last 50 years, which led to hunger for more than 60 million people. In 2015, equatorial waters were warmer than usual for the entire year. The central part of the ocean then warmed up by almost 37.4 degrees Fahrenheit at its peak in November, and the overall warming temperature was 35 degrees Fahrenheit, which is likely to be a record value since 1860. All continents have been affected by El Niño, directly or not. For example, Australia experienced severe droughts, especially in its eastern and northern parts. This resulted in an early start to the fire season on the continent, with a total of 125 fires. The fire severely damaged large areas of nature in Tasmania, including rainforests and swamps that had hardly ever experienced fires before. Moreover, the worst coral bleaching was recorded during this period, a process that causes corals to turn white and become very vulnerable to death. The spring and fall of 2016 in Australia were among the driest on record, so the harvest was significantly affected. In addition, the heat reduced supplies of ore, the most exported commodity. Regions in Asia also suffered from different weather conditions. For example, 85% of the Philippines and Indonesia experienced severe drought. Large-scale fires broke out in Indonesia, which worsened the air quality in neighboring areas, including Singapore, Malaysia, Thailand, and others. The fires also affected the export of palm oil, which led to higher prices for the product and, as a result, for all food that used the oil. In addition, rice production in Vietnam and Thailand has dropped significantly, in particular due to water shortages. India, in turn, has reduced its supplies of rice, sugar, cotton, and corn. The northern regions of China suffered from droughts, while the southern regions were affected by rain and floods. South America has been severely affected by weather-related disasters in all regions. In 2016, Peru experienced severe flooding and landslides, causing about 5,000 people to lose their homes and reducing shrimp production. Moreover, 150,000 people had to be evacuated from flooded areas in Paraguay, Brazil, Argentina, etc. In addition, Argentina experienced one of the largest locust infestations, which severely worsened the state of agriculture in the country. Adding to this, the return of rains in April 2016. In Colombia, famine started due to droughts. About 2.3 million people needed humanitarian aid, according to the UN. In the Caribbean, there was a shortage of drinking water. St. Lucia even declared a state of emergency in the country. The varying impact of El Niño in Brazil led to a sharp rise in coffee and sugar prices around the world. The United States and European countries, on the other hand, hardly felt the direct impact of El Niño. The states of Missouri, Mississippi, and the United Kingdom received more precipitation than average, but this didn't seriously affect their economies. And finally, the African continent also suffered economically from this phenomenon. Food production in South Africa fell by 6 million tons. In some parts of Zimbabwe, 75% of the harvest was lost. 10 million people in Ethiopia needed humanitarian aid, and about 458,000 children were treated for acute malnutrition. In total, 60 million people around the world suffered from hunger. In addition, unfavorable weather events led to disease outbreaks, especially in Africa and South America. Thus, due to floods in several countries of South America, the Zika virus began to spread, and in Africa, outbreaks of cholera and Rift Valley fever in the east of the continent, as well as malaria, were recorded. In particular, animals suffered from the effects of El Niño, such as marine birds or small mammals, which sometimes causes predators to attack farm livestock. The populations of invasive species, such as locust and tree frogs, have also increased, spoiling crops and increasing the spread of dangerous diseases. We should not underestimate the seriousness of the danger brought by El Niño and La Niña. Meteorologists are already recording signs of El Niño, which is very likely to begin in late summer 2023 or very early in 2024. According to the National Oceanic and Atmospheric Administration, researcher Dylan Amaya and World Meteorological Organization Secretary General Petteri Talas, we may set new global temperature records next year. One of the reasons for the sharpness was the very long La Niña period, which has lasted 3 years and only ended in March. So a lot of heat energy has accumulated in the ocean, and therefore, after the cold snap, all this heat will be released, which will strengthen the effects of El Niño. It is still difficult to say whether the 2015-16 scenario will be repeated, as there are no two El Niños alike due to the difference in the periods of this phenomenon and the overall climate situation on Earth. However, there are already several forecasts of what to expect from the upcoming El Niño. A candidate in climate science at Tracasca Castro names 4 possible consequences for global weather in 2023-2024. First, it's possible that the ocean temperature could rise to 35 degrees Fahrenheit. Moreover, during its peak, temperatures may rise even more, as they did in 2015 and 16, but according to this researcher, it's too early to predict how severe this temperature increase will be. Secondly, after a long period of La Niña, Australia has had a lot of rainfall, but this could all change next year. As the overall temperature on the continent has increased by 34.5 degrees Fahrenheit compared to the beginning of the 20th century, a new super hot year could cause early fires. Thirdly, not only could a humanitarian catastrophe recur in South America, but outbreaks of serious diseases like malaria, the Zika virus, or dengue fever, it could reemerge. And even birth disorders and miscarriages due to abnormal heat could spread. In addition, the Amazon rainforest, as well as those in Africa, India, and Australia, may experience severe droughts which will reduce the growth of vegetation and, as a result, less CO2 would be absorbed from the atmosphere. And fourth, Northern Europe can expect cold, dry winters, while Southern Europe can expect increased precipitation. In particular, the North Atlantic may experience a cold snap. During El Niño, access to food and drinking water becomes more acute, so there will probably be no exception this time. Australia, Brazil, Peru, Africa, etc., all of these countries and continents that had a hard time with their dramatic climate change in 2015 and 16 may, unfortunately, experience a severe food and economic crisis again. It's also possible that exports of many agricultural and livestock products, as well as mining and fuel products, will decline dramatically, with an indirect impact on the entire world. NOAA also suggests that the United States may suffer from a strong increase in precipitation in the eastern part of the country and a strong heat wave in the southwest and south. A study by researchers at Dartmouth University, led by Christopher Callahan, estimates that the effects of this phenomenon will cost the global economy about $3.4 trillion over the next 5 years. Thus, the second half of 2023 and next year could be extremely difficult periods for the entire world. However, El Niño and La Niña will not stop there. There is a possibility that in the future they become more serious, more frequent. In particular, these two weather events may disrupt the formation of tropical forest in the future. However, one of the main drivers of the increasing impact of El Niño and La Niña is a greenhouse gas emission, which further warm the panel. Therefore, in the long run, we can expect that high global temperatures may become the norm and continue to rise, which will become an even greater threat to the world. The possible future deterioration of the weather situation on the planet is a signal to all of us, because only taking care of the environment can protect us from catastrophic consequences.